Welcome back to second lab of real time digital signal processing. As I was mentioning in the first lab, so anybody is ready to dirty their hand, so you can start doing it. So, we will start with first in this lab sine generation. So, what is it? As a recap, we discussed how to use Code Composer Studio and for dot products and then sine generator what we did. Today we will see that only one sine wave generation, last class we have seen. So, we have multiple ways of representing sine generation. So, we will be using both Matlab and then Code Composer Studio today, and then how to create a basic music. So, people who are music lovers, you can create your own music and then hear how it is going to come. So, the first sine generation, what we will say it as direct digital synthesizer technique. So, in this case we will have variable initialization section, that is we say lines 2 to 6 here. So, we will be initializing our amplitude as 32,000, signal amplitude what we call it. So, compared to this detail on the left hand side, the code is given on the right hand side for Matlab implementation, and some coarse function are constrained to the range between plus or minus 1, which requires an amplitude scale factor of A, what we call it, or the DAC output whenever we want to output it onto DAC of our board, then we have to enhance the amplitude of it. For that we have taken some amplitude equal to 32,000 in this case. So, we use the tiny portion of the full range of what we call it as plus 32767 to minus 32768. I think there should be an alarm ringing in your thing. So, we are using the 16-bit signed representation in this case. So, the number of bit for the fractional representation what we will be using is 15 bits, 1 for sine bit. So, for a constant output frequency, the calculation of the phase increment, that is what is shown in line here, phase enhancement which is given by the equation 2 times pi into frequency component what it is chosen f as 1000, that is 1 kilohertz here, divided by the sampling frequency. In this case sampling frequency fs is assumed as 48 kilohertz. So, we will be calculating the phase increment based on this unit, and for a constant output frequency, the calculation of phase increment as we said in line 9, the calculated value of the phase increment must be, usually we restrict between minus pi to pi, here that is what it will be less than or equal to pi, or signal aliasing is going to happen. So, for that reason, so you will be seeing the actual algorithm to generate our sinusoidal signal requires only 3 lines of code, that what you are seeing line 13 to or 15 basically is the code to generate our sine wave in this case. Rest of them are initialization functions. So, inside a for loop and then simulate the execution of interrupt service routine in C if we are writing it. We will consider this writing of interrupt service routine in the next lab class, that is called each time a new sample is going to arrive. So, these lines of code accomplish the following 3 tasks each time an interrupt service routine is going to be called. What is the first one? That is line 13 basically. So, you are adding the phase increments value to the phase accumulator, and then in the line 14 you will be calculating, perform a modulus basically, that is a 2 pi operation to keep the phase accumulator in the range 0 to 2 pi. Either you can have minus pi to pi or 0 to 2 pi is the range what we are going to take it. Here in this case we will be seeing that if it is going to cross 2 pi, then output is going to be modulo value what we will be taking it. In the line 15, we will calculate the system's output value by scaling the sine of the phase accumulator value by A. So, that is what we are going to do in the thing. Just we will see that how this is going to run. So, we will run the Matlab code in this case. So, we have you will be seeing the code Sine Generation .m using the DDS method. So, you will be seeing that your magnitude A in this case I can assume 1, or there it was 32,000, we can vary, we will see it in a while. And then my frequency component what I want is 1 kilohertz frequency what I want to generate. This is a variable, so you can play around with it. And then you will be initializing your accumulator, that is phase accumulator, as 0 and sampling frequency 48 kilohertz. So, this also you can vary depending on your requirement. And then your this thing number of terms, what in this case we are generating 50. This also if you want more waves, basically you can increase that. That is what it says is calculate this number of terms basically. And then calculated and then output terms are going to be your phase increment. This is the increment what we are providing it. So, the phase increment, and this is the one loop what it is going to be implemented. So, for I is equal to 1 to number of terms, because we need 50 terms. So, we are accomplishing this one. So, instead of putting it on the DAC, here what I am doing is I am going to store the output in a loop basically array, which is given by this equation. And then if you have to have the interrupt service routine algorithm for the sine loop, we will be providing it here, and then this output will be going through the interrupt service routine to our DAC output in the real time scenario. So, here at the end of our routine, we can plot and see whether I am able to generate using this function. So, what Matlab does is any of the Matlab version you can take it. In this case I am using Matlab 2020B version. So, you can use any one of them. So, when I run this code, so you will be seeing that. So, my sine generation is running. So, the 50 samples is the output what I have given. So, you will be seeing that you are getting a complete one period of 50 samples here. So, by varying this value, this is one way of generating our sine wave. So, if I increase my magnitude to whatever was given in that, I can do it as 32,000. So, okay. So, I can rerun my code. So, you will be seeing that the magnitude which was 1 in the earlier case, it has gone up to 10 power 4 in this case. So, if you want to change your sampling frequency and the frequency part of it, so you can vary here. F can be, I can give it as here now 2000 hertz basically, and sampling frequency I can keep it at 8000 hertz also, because I have been meeting my whatever the sampling theorem says twice that of the maximum frequency. So, Fn is 2000, which is greater than or equal to twice that of it. So, I am little more than the thing. So, I can rerun this code as you will be seeing it. So, you are able to get 2000 hertz whatever. So, how do you know that you have got the 2000 hertz signal? So, you have to wait for FFT class, or you can run, if you are comfortable with Matlab, you can put the FFT magnitude. If you calculate the thing, you will be getting the, as we can see that So, we can rerun the thing. Okay. So, you will be seeing that my FFT function has a what is it, error in the thing. So, you can go back and then correct it and then see that you will be getting your magnitude function. So, what is the frequency you have represented. So, coming back to my slide, what is the other method of running our generating our sine wave. So, this was the first one, that is direct digital synthesizer what we have taken. Next one can be using a table lookup technique. So, how do you generate your table? So, as you can see in the right hand side here, so you have the signal represented as 32,000, 0, minus 32,000 and then 0. That is, we call it as a cosine signal values. So, what you have chosen f is by 4 case what we have taken the thing. So, coming with the thing, it is a variable initialization section, that is what lines 2 to 4 on the right hand side what it is going to be. So, what it will take, and then we will be establish the code and then variable signal that stores the required values of the output signal, and then you will be reusing them. So, what is that? We will be doing the period determination from the line 7, as you can see it is n is equal to length of signal what you have taken the thing. So, we will be period determination is done by this code, and then actual algorithm to generate our continuous sinusoidal signal is again lies from 11 to 15. So, you are checking whether index has increased to n plus 1. So, what the range we want is 1 to n. So, length of the signal. So, if it is exceeded n plus 1, then you will be starting index again from 1. So, this will be if statement what we will be using it, and then my for loop is going to end here, and then output is going to be signal of index, and then index you will be incrementing it by 1. So, your interrupt service routine can be written here, and then we will be ending the code for the for loop basically. So, we will go back and then see again in Matlab whether it is running correctly or not. So, I have chosen this. So, you will be seeing that signal is represented by these values and index is 1 and number of terms also I have chosen in this case 50, and then n is going to be length of signal whatever you have chosen, and then for I is equal to 1 to number of our terms. So, this code is going to be repeated. If n is greater than or index is greater than n, for the n plus 1 index will be reset to 1, and output again putting it in an array, so that we can plot it and then see whether we are getting it correctly. So, we will run the code. So, you will be seeing that it has generated our sine wave, as you can see in this case. So, this is how second method what you can run with a lookup table. So, it is going to help us that you have pre-calculated and then kept the thing. So, it depends on how much memory what you need it. So, just as I was telling, so to generate using the sine concept, can we generate a musical note? In this case, basic of music what I have taken, it is Carnatic music whatever you call it, it is Saregamapada Nisa what we will be generating it. So, what is the thing is going to happen, we will set the sampling frequency as 8000 hertz, and then T will be varying between 1 and then Fs, and my Sa note what we have chosen, the basic note in this case is 440 hertz. So, that is what we put here, and then will be generating the notes. The next note is, as you can see, is 494. Either you can use the equation whatever the musical literature gives and then do it, or if you have pre-calculated, I can select the frequency part of it for all the note. So, in this case Ga is going with 554 and then Ma will be going with 587 and then Pa with 660 and Da with 698 and then Ni will be 784 and then the last note, as you know, it will be twice that of the first whatever base note what you have taken the thing, which is going to be 88 hertz. So, and then what we do is we will be concatenating them, that is all of them will be horizontal concatenation is going to happen. So, we have the function horizontal cat actually all these notes and then we will be playing that. So, just hold on a while. So, we will see how our music is going to come out of it. So, this is the code written. So, if you want you can treat it nicely and then say that with the comments what you can put the thing. So, here basic thing what I wanted to show in this lecture. So, go to the editor. So, you will be running this. So, you will be hearing it and then you have to comment whether you have heard the Sarigama Padanisa correctly or not. Want to hear it once again? I will play the thing. So, if you have your notes basically, some of the students played their own happy birthday song and then our national anthem. So, which we can play when everybody is around. So, you can go and then write your own musical compositions and then generate it and hear that you are getting it correctly. So, the other way of doing it is whether I can do sine generation using my polynomial approximation. We call it as GNU math library here. So, this is the approach using the scientific library which stores the first 11 coefficients of the approximation. So, what it calls is harness form is used. What is that harness form? We will see it once now. The number of operations required in this case is a to the power of 10 into 10 plus a power 9 into 9 plus a power 8 into 8 plus etc. So, this will be a power 0. So, you will be seeing that how the harness form is going to be. You will be doing a power 10 into your this thing. What is it? 0x, x is the input value what you have to give it, plus a power 9 into x. So, and then plus a power 8 into x. So, so on what you will be putting the thing. So, that your power calculation is going to be reduced plus a 0 what you will be doing. So, to generate sinusoid of frequency f naught, we need only few stage for each steps for each sample. So, you will be calculating the cos theta via the approximation above and then send the value to the DAC and then increment theta by omega naught is equal to 2 pi f naught by fs and then check if theta is going to exceed 2 pi f basically, then 2 pi, if it does, subtract 2 pi to prevent the overflow or loss precision. I want you to write the code for this in Matlab and see whether you have got the sine wave generated correctly using this polynomial approximation. So, what this says is this method produces a very accurate signal, but requires roughly 20 multiplications and 20 additions, as you can see in the bracket there. per sample in addition to the storage of the coefficients. So, you have to store all the coefficients and then run them. And then it is also extremely flexible, since it allows us to change the frequency as we please by simply changing the amount at which we increment theta. So, by doing the theta increment varying, so you will be able to get whatever frequency you want to generate. So, coming to the next one, some of the lab component, we will be seeing that how to generate real time sine wave generation and FIR filters. Enjoyed this sine wave generation and then music generation in Matlab. So, the same thing what we will see in the next lab class on DSP processor. So, you can play with it with whatever music you love. Thank you. So, see you in the next lab session.